Okay, recording has started. First, just to review what we just talked about. To review what we just talked about, as far as our plan for today goes, first I wanted to review the speed and velocity stuff that we introduced yesterday at the end of class. Then I wanted to look at a couple of situations from your outline and then also from the problem set that I gave you yesterday that hopefully will reinforce those concepts. After we do those things, we'll get into the lab. We'll talk about the lab when we get there. Okay. All right. First things are then calendar. Okay. As far as your calendar goes, it is February 29th.
I didn't have my party. Sorry,
unlucky.
guys.
Today is February 29th. There it is. We'll do velocity acceleration calculations. Actually, we're only doing velocity calculations. Then on Friday, we're already sort of behind schedule today, and that's all right. So on Friday, we'll finish up the intro to mechanics thing. So we'll talk about acceleration on Friday and what that means and how it applies. Hopefully, we'll get into some situations dealing with acceleration on Friday. I have quiz scheduled for Friday. Either I'm going to give it to you as a take-home or I might give it to you on Monday. We'll just kind of see how it goes. Okay? So I might give it to you as a take-home over the weekend. Then we'll start getting into the relationship between velocity and acceleration next week. We'll talk about how that goes. That quiz is probably going to get pushed back. No block next week. And we'll talk about next week when we get there. So that's what we're looking at. And then test is probably going to be sometime during this week. Because we're on short periods this week, it might get split up over 2 days. We'll just play.
Nice.
We'll play it by ear. We'll play it by ear and see how that goes. All right. On Monday, we introduced this idea of mechanics. We said mechanics is the study of motion. And we said that when we are studying motion, there are 4 things that we want to know about that object. What are the 4 things that we want to know about that object? Here's the point. Where it is. We talked on Monday about the answers to that question of where it is, right? We said that the answer to where the object is depends on what we really want to know. But some terms that answer that question would be position, displacement, distance traveled. Those all deal with where an object is and how far it's gone and stuff like that. Okay? Yesterday, we introduced the second question, Sam. What was the second question? What is the object doing now? Okay? Before we get into what is the object doing now, the last 2 questions, what will it be doing in the future, and when are all these things occurring, we'll deal with that on Friday. Okay? Well, let's start with where is the object doing now? What is the object doing now? On yesterday, we talked about 2 answers to that question, right? What are the 2 things that can answer the question of what is the object doing right now? Allison, so you can't, you want to. Penny, go ahead.
Magnitude. All right.
Nope.
Direction.
Talk about 2 terms.
Wait,
Speed is one,
oh.
and velocity is the other one. Okay? So, let's talk about speed first. How do we calculate the speed of something?
S equals E over T.
Distance divided by time, or the distance traveled divided by the time it takes to go that distance. We said that speed was a rate. And what did we say a rate was? We said whenever we talk about a rate factor, there's what? There's a time factor, something over time. Okay? Speed is a distance divided by time, or the rate that distance is traveled. Okay? And I believe in class yesterday, we looked at this picture, is that right? Of this girl running the race? Okay. After we talked about speed, we talked about velocity. Okay?
The displacement x over time.
Yeah, the displacement over time, so delta x divided by t. What's the big difference between speed and velocity? Kelly, go ahead.
Velocity also includes the direction.
So that means velocity is what kind of a quantity? A vector quantity. Velocity is a vector quantity, whereas speed is just a scalar quantity. Vector includes both
magnitude and direction.
Right. Vector includes both magnitude and direction. So, Kennedy, when we're talking about velocity, right, velocity is going to tell you 2 things about that motion. What is it going to tell you?
How fast.
How fast and which way it's going. Good. Okay. And that's velocity. Are we good there? For starters? Okay. Let's go here. Let's see what I got here. All right. On your sheets, on your outline sheet, I believe you have these two pictures of this gecko. Is that correct?
Yeah.
Okay. So let's go here, and let's grab this picture of the gecko first.
Is it the gecko?
Yeah, sure.
Cool.
Okay. Sure it is. All right. So here is the first picture of the gecko, and in your outline it says calculate the velocity. Is that correct? Right above the gecko.
Yeah.
Average.
Yesterday, we talked about average velocity and we came up with a definition. Nick, you told it to us. Well, how do we calculate the velocity of something?
It's change of x.
Displacement over time, right? And that's how we calculate the velocity. Nick, how do we calculate the displacement of something? Do you remember?
It's the
Look back. Change in
Isn't it like
position.
it's in second? It's the second position minus.
Good. The second position minus the first position, or final minus initial, right? Divided by the time. Okay? Are we good there? Yep. All right. So let's start plugging numbers into this. Okay? First, what do we say the final position of this gecko is in this picture? Okay, that kind of depends on how you do it. Let's call it 84, 85. Does anybody really care?
85.
Okay. All right, so can't do 84.789. Sorry.
Wait, so is that the formula for velocity?
Yeah, so Allison, this is technically how velocity is defined. Okay, but remember that we talked about that when you calculate the displacement of something, this is how you calculate the displacement of something, right? Does that make sense? So, 85 centimeters. Is that good enough for the final position? No, right? What are we missing, Alex?
Where it's like
Mm,
the initial.
the direction, right? Because it could be 85 centimeters from wherever, right? Where did we say the reference point was in this picture? This is our reference point, right? Okay. So, what are we going to say here as far as 85 centimeters goes? 85 centimeters could go east, could go right. Now, the one thing that's probably going to make this a little bit easier when we do the calculations is if we say positive 85 meters. Okay? Because we'll call that side of the number line positive, the other side negative. Okay? So there's our final position. With that in mind, what's the initial position?
I put 24.
Okay, that's fine. So the initial position is going to be positive 24 centimeters. If you said it was 25 or 23, that's fine. Then, that's going to be divided by the time over which this occurs. And Chris, what was the time? It's going to be 4 seconds based on those two clocks that we have there. Okay?
So, like, the last 85 centimeters, the time will exit, are you sure that's
No, this is this. Because that's where it ends up, right, Allison? Okay, that's the final position. And then the initial position is this one. That's where it started, right? Is that good for now? All right. So now it's just a matter of doing some math, right? Sam, you have a calculator out, correct?
Yeah.
Okay, did you run this through your calculator yet?
It's 61.
Okay, so it's 61 centimeters, right? Technically, we probably should go positive 61 centimeters for a direction, right? Divided by 4 seconds, okay? And that gives you 15.25. And then units, what would our unit on this one be? This one's not in meters, though, right? It's in centimeters per second, okay? Now, is that an SI unit?
No.
It's not the SI unit for velocity, but that's still fine because it's a distance divided by a time.
Do you want us to convert to?
Because this ruler is measured in centimeters, right? And I guess it doesn't really say that, but if it's a meter stick, yeah, you know.
Do you want us to convert it to meters?
Not necessarily, unless I specifically ask for it. At this point in time, it really doesn't matter. Okay?
That happened in one of our homework problems.
What?
That happened in one of our homework problems.
That it did?
Yeah.
Okay.
Yeah,
Unless it specifically asks for it, I really don't care. Now, problem though. Okay? Kennedy, going back to something we talked about before. We said that velocity is what kind of a quantity? What does velocity tell us?
Oh, okay. It tells you how fast or which way.
Okay, not or, tells you how fast and which way. So that makes it a vector quantity. Is this the right answer to this problem? No. What should we put on here? We could go 15.25 centimeters east, Kennedy. Okay. Or if we stay consistent with what we've been doing to take care of the direction, right? Let's call it positive 15.25 centimeters per second. Okay. That means we're going, in this case, Kennedy, towards the right because that's what we've established as our positive direction. Okay? Good so far? Okay.
Follow me more often, 'cause I think I get it when you call on me.
Okay.
No. Well, I get when you call on me. So call on me.
Okay. Gecko picture number 2.
I have a question on the other sheet.
Which other?
Is displaced describing motion?
Let's look at gecko picture number 2.
You don't give us enough room to do all these.
Sorry, I thought I gave you a little bit of room. Sorry.
Well, when you have big hands like me.
All right. Gecko picture number 2. Once again, calculate the average velocity. So we're going to start off like this. That's how we define average velocity. And we said that displacement, in order to calculate the displacement of something, we need to know its final position minus its initial position. Okay? Good there? Okay. Now, let's start putting numbers in, right? So, what's the final position of this gecko?
I say 14.
I'll go 12.
Oh, it's 12.
It is not 12. It's definitely 14.
No, it's like 14. 14. 14.
All right, hey, seeing as how there's uncertainty in measurement, it really doesn't matter what you write down, right? You can write down any number you want here. Well, not any number, but 12, 13, 14, any of them would work, okay? But it is important, right? Because this is a position, what side of the reference point are we still on? We're still on the positive side. Because, Allison, we've called this our reference point, right? It's 0, okay? We're just like a number line, right? We're going to call everything to the right of 0 positive and everything to the left of 0 negative. Just like a number line.
It doesn't even matter if you're going back, if you're still
Hold on 1 second to that question, okay? So here. So final position, positive 14 centimeters. Minus the initial position.
78.
79, 8.
78.
I'll go 78. Okay? But once again, what side of the reference point are we still on? We're still on the positive side, so it's positive 78 centimeters.
So negative would only be...
Hold on.
Final minus
Hold on.
initial.
So, let's answer the questions. Alex, okay? We would only have negative positions if this gecko was somewhere like over here.
But it can't go to negative.
Well, it can go in the negative. We just don't have a ruler there right now. So it could. That would be fine. It's just that anything, if the gecko was somewhere over on this side, then we would have negative positions. Okay? That's for position. Because remember, position tells you where that object is. Right? Now, to finish off this problem, okay? Final position, 14 centimeters, positive. Initial position, positive 78 centimeters. What's the time frame that goes by here? 3 seconds.
But I thought it was 7.
Wait,
I thought you had to go around the...
oh.
Starts at 6, ends at 9, right?
Oh, I was just looking at it.
So there's the initial time, there's the final time. Okay? Even though it didn't start at 0 seconds, Kennedy, right? This change in position from where we started to where we finished took place between when the watch was at 6 and when the watch ended up at 9.
It's when this starts right there.
Yeah, see? Alright, so we run this through. Sam, put your calculator out still?
Yeah.
Okay. So, when you do the top of this fraction, what do you end up with?
Negative 64.
Okay, so negative 64 centimeters, right? Divided by 3 seconds. So when you do that,
21.3333.
let's go 21.3. That'll be fine for now. That's centimeters per second. Okay? Alright, so here, let's make some connections, right? Kennedy. Velocity, what kind of a quantity? Vector. So that means it has to tell you what?
How fast?
How fast and which way. Okay? What's different about this gecko picture versus the previous gecko picture? It's moving in the opposite direction. So we have to show that. We show that by the negative sign on the velocity. Okay? Now, let me do this. Okay? Alex, before, we talked about position is negative if it's over here on this side of the 0 point, right? Because position tells us, position answers which question? Where, right? What question does velocity answer, though?
Where and how? What's it doing?
What is it doing now, right? It's still on the positive side of the reference point. But which way is it moving? It's moving back, right, in the negative kind of direction. It hasn't gotten there yet, but it's moving in the negative direction. If we use like directions, right? If we called this east and west, the gecko is still on which side of the reference point? He's still on the east side of the reference point, but which direction is he moving?
West.
Moving west. Does that make sense?
Yeah.
So you can have a positive position with a negative velocity. That just means you're moving in the opposite direction. Does that? I saw a couple hands go up before. Does that answer people's questions? Okay. Miriam, go ahead. Now, for speed, Miriam, we said that speed is just distance traveled, right? Here, when we do this calculation, what's the one thing, we said speed is what kind of a quantity? It's a scalar, so it only tells us what? Direction. No, sorry, not direction. It only tells us what? It only tells us how fast, or magnitude, right? Which in this case would be how fast, okay? So, Miriam, good transition for us, okay? If you go to this problem set that I gave you yesterday, okay? Grab this problem set. On the back of this problem set, there's a section that says velocity and acceleration questions. Okay, on the back side. Yep. So in this, because in the case of speed, the how much is how fast, right? How much is kind of a general term. It just depends on what thing we're talking about.
How much speed?
Yeah, how much speed you have, yeah. Let's take a look at number 1. Okay? So number 1, down there at the bottom, says the speedometer of a car moving east reads 100 kilometers per hour. The speedometer of a car moving west reads 100 kilometers per hour. Compare and contrast the speed of the cars and the velocity of the cars. In your little 2-3 person groups, take 30 seconds to discuss. Go.
Oh, yeah.
One's going to be positive, one's going to be negative.
Velocity is like, wait, so reference point started from? So I mean,
They could both have the same reference.
you have to say that there was one opposite.
Because remember the velocity, direction of velocity tells you which way it's going, not necessarily where it is. They could be right next to each other. One could be going this way, one could be going this way. They would both have positive positions. Remember, position tells you where, but negative one would have positive. All right. Yeah, okay. But then you might get different answers. If they both have the same reference point, the same frame of reference, that's what you do. All right, so let's discuss. So I heard a lot of people discussing relevantly. Okay. The correct answer to this question is. They have the same speed, but they have a different velocity. Okay? Because speed is what kind of a quantity? A scalar, which means it only tells you magnitude. They're both traveling the same speed. They're both going exactly the same how fast, right? But velocity, Kennedy, is what kind of a quantity?
Vector.
Vector, so it tells you both.
How much speed and then where you're going.
Right. The little thing in your car that's right behind the steering wheel, right? That tells you how fast you're going. We call it a speedometer. Is it a speedometer?
Yeah.
It tells you how fast you're going,
So it's no.
but what doesn't it tell you?
The direction.
It doesn't tell you which direction. So is it a speedometer or is it a velocimeter? It's a speedometer, because if it was a velocity meter, it would tell you which way you're going as well. So some cars have a little direction thing, and that gauge together with that would make it a velocity meter, a velocimeter. Velocimeter. All right. Where do I want to go next? On that same problem set, number two. It says during a certain period of time, the speedometer of a car on cruise control reads 60 kilometers per hour. Does this mean the car had a constant speed? Does this mean the car had a constant velocity? Discuss. Go. So the limit says the car, so it goes. You don't have to press the gas.
It doesn't mean any of them.
All right. So, for this question, during a certain period of time, the speedometer of a car on cruise control reads 60. Does that mean the car has constant speed?
Yeah.
Yes, because it continues going the same how fast. Does it mean the car had a constant velocity?
No.
Not
You don't know
necessarily.
if it's going east or west or north.
Or, Sam, just because you don't know that it is going which direction, more importantly, though, if it was to have a constant velocity during that entire time, it would have to be going the same direction. It doesn't matter which direction it's going to have a constant velocity, it would just have to keep going the same direction. Does that make sense? So, Sam, if you're on the highway, does the road always go exactly straight?
No. Oh,
No,
yeah,
right?
yeah.
But if you were like in Nebraska, right? Anybody ever driven through Nebraska before? I never have, but I've talked to people who have, and it's just like a road with cornfields on both sides. Like, no, absolutely not.
No, when you go to Muskegon, it's down like 60.
It is not
Yeah,
straight.
when you're going to
Stuff like that.
oh, you mean
You guys don't know what.
You mean straight.
Yeah,
No, but so it's just like straight and that's
that would be a constant velocity because you're going the same speed, but also the same direction.
But what if you're on the same road and you're like twisting? Is that still the same velocity?
No, because Sam, when you're twisting, right, if I'm going 60 kilometers per hour north, and then the road turns, and now I'm going 60 kilometers per hour northwest, right?
Yeah.
That's not the same velocity.
Okay.
Because velocity tells you how fast, but also which way.
Right, and so like the only way for this to be the same, for this to, like the only way for this to be like the same constant velocity is if it's going in a straight line like the first.
Yes. Lauren, go ahead.
Were we considering direct right by like north-south?
At this point, yes, okay? Because, Lauren, yesterday, did we talk about one-dimensional motion versus two-dimensional motion? Okay. Let's go back to this picture. Yep. It's not a plane, it's a line. So this, Lauren, this picture of this gecko is moving in one dimension, okay? In one dimension is just a line. In one dimension, you only have two choices as far as direction is concerned. You're either moving this way or you're moving that way. And that's why we can use positive and negative in one dimension to distinguish this direction from the other direction. Okay? When you get into two dimensions, which is like an XY axis, now positive and negative don't really work because are you positive on the x-axis or positive on the y-axis? So we have to come up with another way to distinguish direction. A lot of times we'll do north, south, east, and west if it's appropriate, but maybe not. Okay? Once you get into the real world and you start talking about having three dimensions, right, an x, a y, and a z-axis, now we have to come up with an even different way to distinguish direction, but we're not going to go there now. So.
If you have like an incline or something, so you know how it's like you're still traveling, you know, like say 50 meters, but if you just have a line, it's going to line.
Yep.
45.
True.
Is that would you just say like it's 50 over distance traveled, or would that be 45?
It really depends on what you're it really depends on what you want to know. If you want to know like the distance it traveled like along that path, or do you want to know how far it went east or how far it went north? Does that make sense?
Yeah,
Because it's not north, but it is up and sideways. Does that make sense? So whereas north, south, east, and west might be moving along the x-axis, the y-axis, and the z-axis, or the x-axis, the y-axis, an incline might be like the z-axis, kind of like throwing that in there. That's past really what we're going to do in here. So, but the positive and negative works good if we have one dimension, which is basically just a line, and that's where we're going to start. Okay, is that good for now? All right. Are we good with these questions? Good for now? Okay. All right. Next thing we're going to do, we'll work on that. We will work with a little bit more on Friday, and we'll introduce something new. We'll introduce acceleration on Friday. But what I want to do now is I want to run through the lab with you guys, talk about what we're going to do and where we're going to go with it, okay? All right.